Now here's an example of a two-dimensional electrostatic force question where we again use proportions and some basic geometry laws to save ourselves a whole lot of calculation. The setup for this one is four identical positive charges at the corners of a square. And the charges are labeled A, B, C, and D. So what you're given in this one is that the force between A and B is called F, and then we want to know how large the force will be on charge A from all three charges. So I'm going to represent the force on A with little vector arrows, because the vector arrows definitely help us organize things a little bit better. So what we're given is that there is a force F caused by charge B, and it must be a repulsive charge because these are two positives. That must mean because charge D is the same distance away, it would exert the same amount of force, but its repulsion would be straight down. So I will label that one F and draw it with the same length I drew the first one. Now, here's where a little basic geometry rule comes in. If the sides of this square is called D, then the diagonal across this would be D times the square root of 2. So, using the inverse square relationship between distance and force, being a distance of D radical 2 instead of just D means we have a force that is half as big as the other two are, and of course it would be repulsive down at 45 degrees. And again, we're using the inverse square relationship between distance and force. So increasing it by radical 2 will decrease the force by radical 2 squared, which of course is half. So we'll label this 1/2 of F. And so those three vectors represent the three individual forces. Now the idea of superposition means that the force on charge A is just the vector sum of those three individual forces. So now if we arrange these in a logical fashion, what I would probably do is add the two perpendicular ones first, because that's going to form a nice right triangle, which is isosceles. So when we add two identical vectors that are perpendicular to each other, again using that same little geometry rule, we get a net force from those two of F times radical 2. Now so far that's just the two larger forces added together. Now we need to add in the contribution from charge C, which is 1/2 of F, and what's nice about this is it's already in that 45-degree direction. So what I'm going to do is I'm just going to add it on right down here. We'll call that 1/2 of F. And so here are the three forces. I'll outline it in red. The three individual forces, 1, 2, 3, but the logical way to add them is to treat the first two as just their resultant, and then we add in the contribution of the last one. So I don't know if there's a great way to write this simply, but since we're just looking for an expression in terms of F, I might write it's the sum of radical 2 plus 1/2 times F.